Hi everyone, today I'm going to present our work MITFAS, Mutual Information-Based Temporal Feature Alignment and Sampling for Area Video Action Recognition. For UAV videos, there are many challenges. First, in most time, drones are flying at a high altitude, so the target actors appear significantly small, which results in less useful information. Second, depending on the flying altitude of the drones, the human actor may appear dramatically different in terms of size and scale, which makes it hard to extract features for model training. Third, the drones are flying dynamically, so there is more background changes than human behavior, which makes it easier for the model to focus on the background, but the model should focus more on the target actor. Researchers try to crop the target and then do the action recognition. This is a promising way, but the problem is that cropping frames directly based on bounding box may lead to inconsistent or shaky video streams. This inconsistency can arise from variations in the detector's performance and the different pose of the individual within the frames. Here, we propose mutual information-based temporal feature alignment and sampling for area video action recognition, called MITFAS, to solve those issues. First, we've introduced the mutual information a bit. Mutual information is a concept in information theory that essentially measures the amount of information given by one variable when observing another variable. IXY is mutual information and H means entropy function. Hx and Hy correspond to the entropy of x and y, which quantifies the complexity of all possible outcomes of x or y. Hxy is a giant entropy that examines the overall randomness given both x and y. The giant entropy Hx and y is minimized if only if there is a one-to-one mapping function between x and y. It increases when the inherent statistical relationship between x and y weakens. Maximizing the mutual information between two images or regions tends to find the most complexity overlapping area by maximizing the individual entropy, such that at the same time they explain each other well by minimizing the giant entropy. For our method, we have MI alignment and sampling. For alignment, given a starting frame ft in a UV video, we use a localization network to localize the human and crop the region containing the human motion as a reference image FR. At time t+1, we estimate the optimal operation parameter omega t+1, which contains rotation, translation, and scaling, such that the mutual information between the region we got from ft+1 after omega t+1 and the reference image FR is maximized. In other words, we try to generate the corresponding region in t+1 such that it is most similar to the reference image in the way that the pixel pairs in both images are well matched and aligned. And then we use the region we got in ft+1 as a reference image at the same t+2 and so on. After that, we do MI sampling and action recognition. Here is some visualization for the alignment. As you can see, after alignment, the cropped videos are more consistent and not that shaking. Also, because of the UV's motion, the position of the human actor in ft+1 appears to be relatively behind compared to ft, as you can see the image in the right. Our algorithm computes and aligns those regions so that the recombination models will inform more from the human motions. As shown in the right image, the main body of the human actor in two frames overlapped after feature alignment. For sampling, we sample the I+1 frame from the candidate pool by choosing the frame that is not only least similar to the previous frame, but also all the previous sampled frames, so the model could have more unseen features. Here we show some results on different kind of benchmarks. For results on UV human, given as the resolution size 224 by 224 resolution and 16 frames input, when training from scratch, our approach achieves a 16.2% improvement over the baseline X3D medium and 12.6% over the current state-of-the-art FAR for 520 by 520 resolution and 8 frames input. MITFAS overperforms the current state-of-the-art FAR by 9.6% when training from scratch. For 224 by 224 resolution and 16 frames input when initializing with the kinetics pre-trained weights, MITFAS improves the top one accuracy over baseline by 20.2% and over SOTA method by 18.9%. For resolution over 620 by 620 and 8 frames input, when initializing with kinetics pre-trained weights, MITFAS overperforms the current state-of-the-art FAR by 7.5%. Our method obtains better performance in all settings, which illustrates the effectiveness of our proposed MITFAS. And we also test our method on drone action and NEC drones. Our approach outperforms the current SOTA FAR on NEC drone by 7.2%. Note that the improvement we achieved is obtained with only half input frame size compared with FAR. For on the drone action, we achieved 100% top one accuracy, which outperforms current SOTA by 7.3%. We also conduct some ablation studies. As shown in Table 5, compared with other sampling methods, our mutual information sampling results in 0.6 to 6.4% improvement in top one accuracy for UV videos, which demonstrating the effectiveness of our mutual information sampling method. We also compared the result of using mutual information with other similarity measure in table 8. The results demonstrate that mutual information is a better criterion for measuring the similarity between images for UV videos. Thank you for your listening. If you have any problem, please feel free to email us. Thank you.